Okay, so most of the time these table problems are calculator inactive, but there is a group of them that do become calculator active, and it's typically when they put a context with the problem. So in this case, we're talking about the temperature of water in a tub, and it is a strictly increasing. Remember, I mentioned yesterday we didn't end up using it. They told us that it was strictly increasing. We never used that information, but we may use it today. So strictly increasing, twice differentiable function. So remember, a lot of times that comes into play with some explanation where the W of T is measured in degrees Fahrenheit and T is measured in minutes. Notice they give us, well, it's in the table too, but at time equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes beginning at time 0. And they give us values of the temperature for the first 20 minutes. All right, so part A says use the data in the table to estimate W prime of 12. Show the computations that lead to your answer. Use correct units. Interpret the meaning. So we need to give that number. We need to show the computations, and we need to interpret the meaning as well. So usually that means we're at least talking about 2 points here. So estimating the derivative at the point, remember we just do this slope as close to that point as we can get. So we're going to use the data for time 9 and time 15. So W prime of 12 is approximately, now you don't necessarily need to write out this part, but it never hurts to be specific. W of 15 minus W of 9 over 15 minus 9. And the data from the table says that 67.9 minus 61.8 over 6. It is calculator active. What? Yeah, that's fine. If you just jump to the numbers, that's fine. Yeah. It's calculator active. I know these aren't difficult numbers to subtract, but why risk making the mistake? Don't do it. Just go ahead and plug that into your calculator, and you get 1.016 if you truncate, or 1.7 if you round. They will accept either one. So there's 1.4, that is your estimate, and we need to interpret that. We need to interpret that. So we're talking about a derivative, so we're talking about the rate. W is the temperature of the water. So we can say the water in the tub, or the temperature of the water in the tub. The temperature of the water in the tub is increasing because it's positive at a rate of 1.016. Let's talk about units. So that is the temperature. That's in degrees Fahrenheit. What's our unit of time? Minutes. And you can say at time 12 minutes to be more specific, because that doesn't apply everywhere. That is just at this specific time of 12. Okay, so you get 1 point for your interpretation with the units. So it doesn't matter if you interpret it correctly. If you mess up the units, you don't get that point. So just be very careful with that. If you're struggling with figuring out your units, go back to your computation. What was on top? On top was your temperature, that's in degrees Fahrenheit. On the bottom was your time. It's not squared because we just did it once. Okay, this is not the second derivative, so it is just degrees Fahrenheit per minute. All right, use the data in the table to evaluate the integral from 0 to 20 of W prime of T dt using correct units. Interpret the meaning and the context of this problem. All right, so the integral of a derivative, they cancel, but we have to plug in the limits. Okay, so the integral from 0 to 20 of w prime dt is equal to w of 20, because the integral and the derivative cancel, so it's just w of 20 minus w of 0. From the table, that is 71 minus 55, so that is 16. So what are we talking about? An integral is always an accumulation. W prime was the rate at which the temperature was changing, so if we accumulate the change in temperature, our answer is how much the temperature in the tub has changed. Since it's positive, that means that the temperature has increased. So there are several different ways that you can say it. The temperature of the water in the tub has increased by 16 degrees Fahrenheit in the first 20 minutes. They say the water has warmed by 16 degrees Fahrenheit over the interval from t equals 0 to t equals 20. Okay, both of those say the same thing. You get 1 point for the value, you get 1 point for your interpretation with units. So this is, we're talking about the original function, so that's why we just have the temperature unit. There's no amount of time, because we're just talking about the original function. All right, part C. Between 0 and 20, the average temperature of the water of the tub is 1 over 20 of the integral from 0 to 20. Use a left Riemann sum with 4 subintervals to approximate it. And is that approximation an overestimate or an underestimate of the average temperature of the water? Okay, so let's start with the Riemann sum. So start with labeling it 1 over 20 from the integral from 1 to 20 of Wt dt is equal to, don't leave out that 1 over 20 from the very beginning. Okay, so the left Riemann sum, we use the left value, 55, times that interval is a length of 4, plus the left value, 57.1, that interval is 5, plus the left value, 61.8, that interval is length 6, and the last one, 67.9, and that last interval is length 5. So would I start with what? To the left. Okay, again, at this point, don't do anything else by hand. Just plug that into your calculator and get the number. You do not need to try and simplify anything. Just get the value from your calculator, 60.79. Okay, now we've got to figure out, is this an overestimation or is this an underestimation? Well, what did they tell us about the function in the very beginning? It is a strictly increasing function. So if you need to go over to the side and sketch it out, go over to the side and sketch it out. So we've got two choices. It can be increasing and concave down, or it can be increasing and concave up. But if we're doing a left-hand approximation, it would appear for the concave down and increasing, it's underestimation, and it doesn't matter if it's concave up. Ooh, that was terrible. Turn into a trapezoid all of a sudden. Okay, it doesn't matter whether it's increasing increasing is the only thing that matters. It doesn't matter whether it's concave up or concave down. It is going to be an underestimation. So the second part of this problem is to say this approximation is an underestimate because a left Riemann sum is used, and W of t is strictly increasing. That's all you need to say about it. You used a left Riemann sum, and it's strictly increasing. The function is strictly increasing. So you get 1 point. They always say 1 point for the left Riemann sum. So I'm assuming that's the setup, showing your work. You get 1 point for the actual approximation, and you get 1 point for the underestimate with the reason. So that's a 3-point part right there. We have 7 out of the 9 points so far. Let's look at the last one. Between time 20 and 25, the function w that models the water temperature has a first derivative given by that function with a square root and a cosine. Based on the model, what is the temperature of the water at time 25? So they're saying the table ends at time 20. We've got this new function that represents the change in the water temperature because it's a derivative. Okay, so if we want to find the temperature of the water at time 25, W of 25 is equal to, what temperature were we at time 20? 71. Okay, you got to have a starting point, right? It doesn't start at temperature 0, it starts at temperature 71. Plus the integral, excuse me, from 20 to 25 of this new derivative function that they gave us. Don't take the time to copy it down. Just use, they labeled it as W prime of t in the problem. So just use that notation. There's absolutely nothing wrong with it. And then you put that into your calculator. You do not need to try and compute anything else. You just put that in and you get 73.043 when you add it to the 71 where you started. So you get 1 point for your integral expression, and you get 1 point for the answer.